You know, the internet we use every day was built on principles that are really starting to show their age. But what if we could rebuild it, start from scratch, using the most advanced mathematics to solve its deepest, most fundamental problems? Well, that is the incredibly ambitious vision of engineer Ivan Pasev. His work, which he calls Digital Fabrica Theory, isn't just another protocol or another blockchain. No, it's a whole new foundation for our digital world. Think about it. We were all promised this amazing, decentralized, user-owned internet with Web 3.0, but the reality? It's been slow speeds, ridiculously high fees, and this constant threat from new technology just around the corner. So why has this vision fallen so short? The thing is, it's not from a lack of effort. The problem is that we've been trying to build a digital skyscraper on a foundation made of sand. And let's be totally clear about what's at stake here. Right now, the reality is a system that just can't scale. It's basically a sitting duck for the quantum computers that are coming. And honestly, it's often governed by whoever has the most money. It's kind of a dead end. But DFT, it offers a fundamentally different path, a system that's designed for massive scale, with quantum resistance baked right into its DNA, and governance based on mathematical proof, not just the size of your wallet. So, to really get our heads around this huge shift, we're going to follow Pasev's logic step by step. First, we'll look at the big problems he's trying to solve. Then, we'll explore his core idea of a digital fabric. After that, we are diving deep into the 3 mathematical breakthroughs at the heart of the theory. We'll see how they all come together in this stunning 14-dimensional architecture. And finally, we'll look at the actual blueprint for making this all a reality. Okay, so just to recap, what we're really up against are systems that are way too slow for anybody in the mainstream to use, systems that are going to be completely broken by the next generation of computers, and systems that can be controlled by the highest bidder. These are not just little growing pains. These are fatal flaws in the current design. So, instead of trying to patch a broken system, DFT proposes something radical. Let's just weave a new one. The name itself, Digital Fabrica, comes from the Latin word for a workshop or a forge. I want you to picture a master weaver at a loom. They take these simple individual threads, and by following a really precise pattern, they create a fabric that's incredibly strong, complex, and beautiful. Well, DFT aims to do the exact same thing, but with computation. At its very core, the theory treats the simplest units of code, what we call atomic smart contracts, as individual fibers. Now, by weaving these fibers together in mathematically precise ways, we create fabrics. And these fabrics can be entire applications or even whole networks. But the real magic is in what it calls emergent properties. This just means the final fabric isn't just a pile of threads. It has new capabilities, like resilience and scale, that the individual fibers could never, ever have on their own. And this is where that analogy gets incredibly deep and, frankly, just brilliant. Each fiber isn't just some abstract piece of code. It's actually modeled as a physical object with specific properties. So tension represents its computational load. Elasticity is its ability to adapt. Length is its complexity. You get the idea. This isn't just a clever metaphor. It is a rigorous mathematical model that lets us predict exactly how the entire system will behave under stress. So the big question is, how is this new fabric actually woven? Well, the entire theory is built on 3 profound mathematical breakthroughs. And I mean, these aren't just little tweaks. They are completely novel applications of some very advanced mathematics that tackle the biggest challenges in decentralized systems head on. This is really the scientific core of the entire vision. Okay, the first breakthrough tackles the quantum threat. Instead of just sitting around and waiting for quantum computers to break all of our current systems, DSST makes the network itself the defense. The security isn't just in the code, it's in the very shape of the network. The solution comes from this deep, really beautiful area of mathematics called Ramanujan graphs. You can think of these as the most perfectly connected networks that are mathematically possible. They are incredibly efficient for sending information around. But their real genius is this. Trying to find a path through one of these graphs is a type of problem that even quantum computers are believed to be unable to solve efficiently. This makes the network's very structure a fortress against quantum attacks. This property, it's known as optimal spectral expansion, and it's the mathematical guarantee of the network's strength. This little formula is a formal proof that there are no bottlenecks, that information spreads almost instantly, and that the network is unbelievably resilient to any kind of attack. It's basically the mathematical signature of a perfect communications network. The second breakthrough moves on from network security to the messy, very human problem of governance. How do you write rules that are fair, transparent, and absolutely cannot be secretly manipulated? DFT's answer is radical. Just take the ambiguity of human language completely out of the equation and use pure mathematics instead. And the tool for this is not theory. Yeah, a branch of abstract math you would never expect to see in computer science. The idea is to translate every single governance rule, every voting mechanism, every financial policy into a unique mathematical knot. This gives each rule a permanent, verifiable identity that you just can't fake or alter. And here's why this is so incredibly powerful. Every knot has a unique algebraic signature. This means you can take two policy proposals that look totally different, convert them into their knot forms, and then just compare their signatures. If the signatures match, you have mathematical proof that the policies will behave exactly the same way. This makes it impossible to hide loopholes or malicious code in complex governance proposals. You're replacing legal ambiguity with mathematical certainty. It's a game changer. All right, the final breakthrough. This one addresses the problem that everyone is always talking about, scalability. How can a decentralized network possibly handle the demands of a global user base without just grinding to a halt? DFT's solution is called bounded fractal scaling. So instead of a flat network where adding more computers just creates more traffic jams, the network grows like a fractal. You know, like a snowflake or the branches of a tree. New subnetworks branch off from the main one in these self-similar patterns. And the key word here is bounded. This isn't some fantasy of infinite scaling. It's a precise, intelligent architecture that allows for massive, efficient growth, far beyond anything we have today. And this really shows the difference. Old systems, they scale linearly. You add a server, you get a little bit more capacity. A DFT system scales fractally. The metric for this is a Hausdorff dimension of about 1.58. Now, all you really need to know is that this number means for every 1 unit of resources you add, you get more than 1 unit of capacity back. It's a formula for exponential efficiency. So these three breakthroughs, quantum security, verifiable governance, and fractal scaling, they're incredibly powerful on their own. But the true ambition of DFT is to integrate them all into a single, unified framework, a 14-dimensional architecture designed to describe every single aspect of a decentralized system. Now, I know this might look a little intimidating, but the idea is actually pretty simple. This is a complete map of the system's reality, called the canonical layered ontology. It provides a specific layer for absolutely everything, from the prime ethical core that defines truth itself, all the way up to layers that handle policy, communication, and governance. And our mathematical breakthroughs? They slot perfectly into this structure. It's a way of making sure every single component has a defined purpose and a defined place. And this chart makes that abstract idea much more concrete. A concept we all know, like a smart contract, isn't just a piece of code floating around. In this system, it's a specific structure, a hexagonal cell that exists precisely at layers 6 and 10 of the ontology. The governance engine is a zeta voting graph mapped to its own layers. Everything has a home, which creates a system with just incredible order and clarity. So how does this all move from being a theoretical masterpiece to a real-world system that we can actually use? Well, there is a very clear strategic blueprint to turn Digital Fabrica Theory into a new foundational layer of the internet. The roadmap is really pragmatic. It moves from foundation to adoption. So year 1 is all about building the core framework and proving the concept with institutional partners. From there, the focus shifts to scaling up and creating government partnerships in year 2. And the ultimate goal, by year 5 and beyond, is a fully mature, self-governing ecosystem that is a part of the mainstream internet. This is a plan that is designed for long-term, real-world impact. And just to ground this vision in some tangible terms, the project's plan includes detailed financial modeling. The projected revenue for this ecosystem in year 5 is over $300 million. But look, this number isn't really about profit. It's a measure of the sheer scale of economic activity that you can unlock when you build on a truly scalable and secure decentralized infrastructure. So, we're left with a final, really powerful question. What we've seen today isn't just an improvement on the technology we have now, it's a completely new foundation, built from the ground up using some of the deepest tools in all of mathematics. It's a system designed from its very core to be scalable, to be quantum-proof, and to be verifiably fair. So the question that Ivan Passiv's work poses to all of us is this: are we looking at the mathematical blueprint for the next internet?